In the realm of data exploration and model training, defining the search space is a critical step. The search space encompasses all possible configurations that a model can take during the training process. This includes hyperparameters, feature selections, and model architectures. By carefully defining the search space, data scientists can ensure that the model training process is both efficient and effective, leading to better performance and more accurate predictions. The search space is crucial because it directly impacts the quality and efficiency of the model training process. A well-defined search space can lead to faster convergence and better model performance, while a poorly defined search space can result in suboptimal models and wasted computational resources. By narrowing down the search space to the most promising configurations, data scientists can focus their efforts on the most relevant areas, improving the overall effectiveness of the model training process. The search space is composed of several key components, including hyperparameters, feature selections, and model architectures. Hyperparameters are the settings that control the training process, such as learning rate, batch size, and number of epochs. Feature selections involve choosing the most relevant features from the dataset to include in the model. Model architectures refer to the structure of the model itself, such as the number of layers and neurons in a neural network. Each of these components plays a crucial role in defining the search space and ultimately determining the success of the model training process. Hyperparameters are a critical component of the search space as they control the training process and can significantly impact model performance. Common hyperparameters include learning rate, batch size, number of epochs, and regularization parameters. By carefully tuning these hyperparameters, data scientists can optimize the training process and improve model performance. Techniques such as grid search, random search, and Bayesian optimization are often used to explore the hyperparameter search space and identify the best configurations. Feature selection is another important aspect of the search space. It involves choosing the most relevant features from the dataset to include in the model. This can help reduce the complexity of the model, improve training efficiency, and enhance model performance. Techniques such as forward selection, backward elimination, and recursive feature elimination are commonly used to explore the feature selection search space. By identifying the most important features, data scientists can create more effective models that are better suited to the task at hand. Model architectures refer to the structure of the model itself, such as the number of layers and neurons in a neural network. This is a crucial component of the search space, as different architectures can lead to vastly different model performances. Techniques such as neural architecture search, NDES, and evolutionary algorithms are often used to explore the model architecture search space. By experimenting with different architectures, data scientists can identify the most effective structures for their specific tasks, leading to better model performance and more accurate predictions. Several techniques are commonly used to explore the search space, including grid search, random search, Bayesian optimization, and evolutionary algorithms. Grid search involves systematically testing all possible combinations of hyperparameters, while random search randomly samples configurations from the search space. Bayesian optimization uses probabilistic models to identify promising configurations, and evolutionary algorithms mimic natural selection to evolve better models over time. Each of these techniques has its own strengths and weaknesses, and the choice of technique depends on the specific requirements of the task at hand. Grid search is a brute force technique that involves systematically testing all possible combinations of hyperparameters within a predefined search space. While this method can be computationally expensive, it ensures that the entire search space is explored, potentially leading to the identification of the optimal configuration. Grid search is particularly useful when the search space is relatively small and the computational resources are sufficient to handle the exhaustive search process. Random search is a more efficient alternative to grid search, as it involves randomly sampling configurations from the search space. This technique can be particularly effective when the search space is large and the computational resources are limited. By randomly exploring different configurations, Random search can often identify promising hyperparameter settings more quickly than grid search. However, it may not guarantee that the optimal configuration is found, as some areas of the search space may be underexplored. Bayesian optimization is a probabilistic technique that uses a surrogate model to predict the performance of different configurations within the search space. By iteratively updating the surrogate model based on observed performance, Bayesian optimization can efficiently identify promising configurations. This technique is particularly useful when the search space is large and the evaluation of each configuration is computationally expensive. Bayesian optimization can often find high-performing configurations more quickly than grid search or random search, making it a popular choice for hyperparameter tuning. Evolutionary algorithms are inspired by the process of natural selection and involve evolving a population of models over time. By iteratively selecting, mutating, and recombining models, evolutionary algorithms can explore the search space and identify high-performing configurations. This technique is particularly useful for exploring complex search spaces, such as those involving model architectures. Evolutionary algorithms can often find innovative solutions that may not be discovered through more traditional search techniques, making them a powerful tool for model optimization. Defining the search space can be challenging, as it requires a deep understanding of the problem domain and the factors that influence model performance. One of the main challenges is balancing the trade-off between exploration and exploitation. While a larger search space allows for more exploration, it can also increase the computational cost and complexity of the search process. Conversely, a smaller search space may limit the potential for discovering high-performing configurations. Data scientists must carefully consider these trade-offs when defining the search space to ensure that the model training process is both efficient and effective. Consider a case study involving the tuning of hyperparameters for a neural network model. The search space includes hyperparameters such as learning rate, batch size, number of epochs, and dropout rate. By using grid search, the data scientist systematically tests all possible combinations of these hyperparameters within a predefined range. After evaluating the performance of each configuration, the data scientist identifies the optimal set of hyperparameters that result in the best model performance. This case study illustrates the importance of defining and exploring the search space to achieve optimal model performance. In another case study, a data scientist is tasked with selecting the most relevant features for a predictive model. The search space includes various combinations of features from the dataset. By using recursive feature elimination, the data scientist iteratively removes the least important features and evaluates the model performance. Through this process, the data scientist identifies the subset of features that result in the best model performance. This case study highlights the importance of feature selection in defining the search space and improving model performance. A third case study involves the exploration of different model architectures for a deep learning task. The search space includes various configurations of layers, neurons, and activation functions. By using Neural Architecture Search, NAS, the data scientist systematically explores different architectures and evaluates their performance. After several iterations, the data scientist identifies the architecture that results in the best model performance. This case study demonstrates the importance of exploring the model architecture search space to identify the most effective structures for specific tasks. To effectively define the search space, data scientists should follow several best practices. First, they should leverage domain knowledge to identify the most relevant hyperparameters, features, and model architectures. Second, they should use a combination of search techniques, such as grid search, random search, and Bayesian optimization, to explore the search space efficiently. Third, they should continuously monitor and evaluate the performance of different configurations to identify the most promising ones. By following these best practices, data scientists can ensure that the search space is well defined and that the model training process is both efficient and effective. Defining the search space is a critical step in the data exploration and model training process. By carefully considering the components of the search space, such as hyperparameters, feature selections, and model architectures, Data scientists can optimize the training process and improve model performance. Techniques such as grid search, random search, Bayesian optimization, and evolutionary algorithms can be used to explore the search space and identify the best configurations. By following best practices and leveraging domain knowledge, data scientists can ensure that the search space is well defined and that the model training process is both efficient and effective.